Recording. Okay, so today we're starting the third topic of our CIE level syllabus. This is actually in sequence of syllabus. This is actually the fourth topic, which is electricity. We are postponing the waste topic for the time being. We're gonna get back to waste topic after the electricity maybe, because this is the concurrent topic with many of the kids' school proceedings. So we're gonna do electricity. Electricity basically has three parts in this chapter. Is this 100%? So electricity, it has core three parts. We have static electricity, we got DC circuits, and last we have practical electricity. What happens is that static electricity is basically about how the charge is created and how charge actually uh, how something can be made into charged and something can be made into discharged, or how do can we charge non-metal stuffs and metallic stuffs differently. And also we have a little bit of discussion about gold leaf electroscope. I just need to find out something or show you something in the same process, that whether we do need to do gold leaf electroscope or not. So just a moment. It would be appearing for the O-level physics 5054 2022. It will be appearing all of us in 2022, right? Yes. So if I just dive into this on the electricity part, wave, here is static electricity. Where did it go? There you are. Have a look. These are the syllabus points of the static electricity chapter. Describe experiments to show electrostatic charging by friction. Explain that charging of solids involves the movement of electrons. State that there are positive and negative charges and that a charge is measured in coulombs. So you just have to know the unit of coulombs. Unit of charge, which is coulomb. State that unlike charges attract and like charges, you have to be able to state those things. So there will be any explanation asked for this, that why do they do that, because that explanation is actually a really far-fetched complex idea of the field theory and stuffs. So you just have to know that this happens. The reason is not yet presented to you. You don't have to bother it for the time being. Describe an electric field as a region in which an electric charge experiences a force. State the duration of line of force and describe simple field patterns. Describe the separation of charges by induction. Discuss the difference between electrical conductors and insulators and state examples of each. State what is meant by earthing a charged object. Describe examples where charging could be a problem. Describe examples where charging is helpful, as example photocopy and industrial precipitator. And that's pretty much it. So within your syllabus, you do not see the existence of gold leaf electroscope or a device like that. Gold leaf electroscope used to be a part of your syllabus, let's say 2 years back. And since then, they have discarded the gold leaf electroscope because what I think not the same people feels like that it's not very important that you should know about this. But one thing that should be mentioned to you, that many of your school teachers might be interested in teaching you that, and if they do, they will set questions about this topic, gold leaf electroscope, in your static electricity chapter. What I highly recommend you kids to do is that whenever your school teacher is teaching you static electricity or they are about to take classes about static electricity, please help them remember that within your syllabus gold leaf electroscope is not mentioned, so that you don't have to learn it and they should not set questions about it. If you're interested to learn it, I can help you and direct you through certain lectures. You can look out for the lectures of the earlier batches of all of us, which is in the another playlist of my YouTube channel, and you can actually look it up as well. But if you don't want to, there is no harm done, as long as you don't have to answer questions about gold leaf electroscope anymore. To be honest, these topics which I mentioned over here are actually substantial enough for you to learn quite a lot about static electricity chapter. So we're going to dive directly into it. The first thing that we have to understand, that the way we know the way atom is made is that at the center we have a small, heavy, dense, highly positively charged object. We call this nucleus. This is highly positively charged. It is made up of protons and neutrons. It's called nucleus. And outside the nucleus, in spherical or elliptical orbits or elliptoid orbits, we have electrons. So the electrons are allowed to move around in designated shells, which are orbits, which are called shells, and so on and so forth. Important point for you to understand is that protons, which are the positively charged particles of an atom, they are stuck within the nucleus. Electrons happens to be around. So in a normal physical process, not nuclear process, in a normal physical process where we are talking about charging, protons would not necessarily come out of the atom and eventually actually move anywhere. Positively charged particles slash protons of an atom, they are stuck within the nucleus, so they are incapable of leaving or entering within an atom. If someone is incapable of leaving from somewhere else, it cannot definitely enter into somewhere else. So the only way any object can become charged, whether positively charged or negatively charged, is by the movement of electrons. The idea is very simple. If you have a neutral object, it would always have equal number of protons and electrons within itself. It is equal. This information is applicable for an atom. This information is in the large scale is also applicable for an object. If an object is said to be neutral, it essentially means it has equal number of protons and electrons. If the object is quite large, then we can say it has roughly equal number of electrons and protons, because for a very large object, a small variation or small difference between electron number and proton number would not actually make it logically charged. It's sort of like the idea of approximation that I told you at the very beginning of the course, that uh, what do we understand by the word negligible? A human hair thickness is negligible for the height of a human. The height of a human is negligible for the measurement of radius of Earth. The diameter of the Earth is negligible for the distance measured from the sun to the Earth, and the entire diameter of solar system is negligible if you consider the diameter of the whole galaxy. So the idea of negligibility is there. So if we have a very large object, we can say rough, and if we say the object is neutral, the proton number and electron number doesn't have to be exactly same, but that would be ideal, that would be best. But if they're even roughly equal, we can still say it's a neutral object. So we're going to talk about that, this idea of our thing, after a while. But in precise words, an object can be said to be neutral if only it has equal number of positive and negative charges, which means if it has equal number of protons and electrons within itself. The way an object can become positively charged is if electrons leave from here. So negative charges leaving an object leaves the object to be positively charged, and the way any object can become positively negatively charged is if electrons enter into that object. So charging of an object will always happen by means of the movement of electrons, and electrons only, nothing else. Electrons leaving makes the object positively charged, electrons entering makes the object negatively charged. In the same way, one thing you also have to understand, that if we are ever trying to neutralize an object means that we have a pre-charged object. We do have an object which is already charged, maybe positively charged or negatively charged. If we want to discharge the object or neutralize the object, we have to provide exactly equal and opposite amount of charge within the body. For example, if an object has 5 plus 5 sorry, if an object has plus 5, I was right, plus in the beginning. If an object has a charge of plus 5e, in this case is the elementary charge amount. This doesn't necessarily mean electron would be looking like this, but writing this much means the amount of charge is 5 times the charge of a single electron, but it is positively charged. If an object has this much charge, it means currently the object has 5 electrons short. It simply doesn't mean it has 5 protons more. It has the same number of protons as it used to have before it got charged. 5 plus 5e would necessarily mean it has 5 electrons less than usual. If you think that, well, it does have 5 electrons more, but then you have to mention compared to what? It has 5 electrons more compared to the number of electrons available. But we prefer not to write in that terms, because this might incur, or this might actually imply that we are trying to mean that protons somehow got increased in number, but that's not the case. We always prefer to talk in terms of electrons. So if an object has a charge of plus 5e, we say this object is lacking 5 electrons from its natural neutral state. And then so to neutralize the object, or to make the object come back to its neutral state, we have to feed this object 5 electrons, and that can bring the object to its whole neutral state once again. Similarly, if an object has some negative charges within itself, then we have to feed same amount of positive charges within it. And now you might wonder, how do we feed positive charge? Well, we do not feed positive charge. If an object is negatively charged, for example, if an object has a negative charge of, let's say, minus 10e, I should not give the electron sign, minus 10e, in this case means the magnitude of electron, then we would understand that there are 10 electrons more than what there should be for it when it was used to be neutral. Then we have to somehow remove electrons from there. So if an object is positively charged, to neutralize it, we have to feed electron, and if an object is negatively charged, we have to remove electrons. So charging or discharging, any type of this type of process will always have to be explained in terms of movement of electrons slash negatively charged particles. We should never even think, let alone writing, we should never even think charging be a process involving positively charged particles. I'm telling you this, but soon after we're going to talk about a historical mistake, and this might mess up your mind after a while, but we're going to see about that as well, which is called the conventional current. Anyway, so that's the primary bit. And from here, we already understand that there are two types of particles, positive charge and negative charge particles. We already know, or you have to just remember that similar charges repel and opposite charges attract. So if you have two objects which are positively charged, then they would repel, or two negatively charged objects will repel. Positive negative or negative positive charges will attract each other. One thing that I would like to discuss to you in one way, this is actually one of the content of an MCQ question that I usually boggle the students with. Have a look at this case. If you have two charged bodies, initially both the charged bodies have a charge of plus q and plus q, and let's say in this case their force is F and F. They are repelling each other at this distance. What if we increase the charge on one of this object and make this one become plus 2q charged, and make this thing, we still keep this one to be only q, so we keep this the same. We increase the positive charge on one object. In this case, how would this force change? What should be the value of this force? Should they be equal? Should they be unequal? Or should one arrow be longer, one arrow be shorter? Or should this arrow be shorter, this arrow be bigger? What do you think should happen?
One force should be longer than the other.
Okay, that's one guess. Good. Anyone else? What do you think? I appreciate you kids are participating in the class because I cannot see your faces. So the only thing that I can have is your visual or written responses, which can make me feel like that, yes, there is actually a class happening. uh, I really appreciate if you kids really put in some participation.
I also the same guess, sir.
দে বুঝি নাই.
I also the same guess. The long way.
Okay, anything else? Maybe not, because many of you are not saying anything, so I guess that you are assuming the same thing. Okay, I'll help you to understand this thing. Kids, try to understand this thing. These two charged particles are repelling each other, so this is applying a force onto this one, this is also applying a force onto each one, this one. These two forces happen to be Newton's third law pair. This is something that I really want you to understand. It is not going to work that these two forces can be unequal. I'll tell you why. The reason this object experiences a force to the outside, because this charge is repelling it by this force, and by logic this is also pushing it on the outer side by a force. You cannot have two different forces. If you want a very simple idea, let me give you a very simple idea in terms of gravity. Let's say here is Earth, here is a ball. You drop the figure, not drawn to scale, obviously. You drop a ball onto the Earth. Let's say the ball now drops onto the Earth. Now think about it. This has a bigger mass, this has a smaller mass. If the ball pushes the Earth by, let's say, 100 Newton, what would be the force applied on the ball by the ground? What should be this force be?
100 Newton.
Can it be different?
No, sir.
Does this force have anything to do with their masses?
No, sir.
Exactly similar scenario. Just because I gave equal charges and equal forces, this is a case of giving you some idea of symmetry, which is leading you to the wrong assumption that that whenever one of the charges is going to get bigger, this force should be larger and that force should be smaller, or maybe the other way around if you think. But these two forces will never be unequal. The forces should always become same. But obviously, because the charge amount got increased at least to 1, so the force should become larger. So this next force that we're going to have, because we have just increased the force of one force, I mean, you do not know Coulomb's law yet, so you shouldn't be able to guess that this force should become simply double. What you should only understand that the new force should be somewhat bigger than the original length. So if the original force was, let's say over here 2 centimeter long, the new force should be, in actual measurement, it should be 4 centimeter long, representing 2F force. But in terms of magnitude, this should be longer than the original force, and this force should be also the same. Both of these forces should increase, not only one, because these are the forces that these two objects exert on each other simultaneously out of the same physical phenomenon, same charges. It is a repulsion between two similar charges, so you cannot have two dissimilar forces. Now you might wonder that this doesn't look right. I mean, for Q and Q and F and F force, we have 2Q, 2F, but Q would also have 2F. The answer is yes, Q would also have 2F, because here's the deal: this force doesn't have anything to do with the dissimilarity of the charges. This force has everything to do with the total effect that they produce onto each other, very much similar to what happened in the gravitational case. Hear me out. We have this ball dropping onto the ground, and at the contact point is making 100 Newton of corner force. In another scenario, if we drop the ball from a much larger height, then it will definitely push the ground with a much bigger force, right? A regular ball dropped from 10 meter and the same ball dropped from 20 meter, they're not going to hit the ground with the same force. The ball that is dropped from a larger height will definitely hit the ground with a bigger force, right? So
Yes, sir.
you see, the amount of force that is involved is not dependent on their masses. It is basically dependent on how much height are you allowing them to fall from, how much distance are you allowing for them to get closer to each other before they contact each other. That is the variable which controls the force value, not the individual masses. Same thing over here. The individual charge amount does not actually determine how much force they're going to exert. The increase of charge will increase the force, but irrespective of that, the force would always be same, because they are Newton's third law pair. এই পার্টটা কি বুঝা গেছে? এই ডিসকাশনটা বুঝা গেছে কি পোলাপান?
Sir.
Yes, sir.
ঠিক আছে, আচ্ছা, এটা গেল একটা লজিক্যাল জিনিস। and then among other things, the next thing that I usually go for is how do we do charging. But before I tell you about charging, I would like to talk about earthing. We use the term earth, EART, earthing. Earthing is not essentially earth. Earthing means an electrical entity. Earth means planet. Sometimes earth also means ground, which means the surface of the planet, but and earth can also mean soil in some other in some context. But earthing is an elliptical term, which means it's an elliptical object. Let me elaborate what earthing essentially means. The definition of earthing goes like this: if an object is so big that it has a huge number of protons and electrons within itself, such that a small addition of electrons or a small deduction of electrons or removal of electrons does not effectively make it charged. The word effectively is key. So if an object is so huge, or it has so many electrons and protons within itself, that a little bit of addition of electrons or a little bit of subtraction of electrons does not effectively make it charged, then we can call that object an earthing. It means that that object has the capability to make any object neutralized by either giving up some electrons or by accepting some electrons from them, but that object will, by its own property, will always remain neutral. So an earthing is in generally at a neutral object, which means it has at 0 volt. Volt is something that we're going to talk about a bit later. It is always neutral. And if we connect a charged object electrically with an earthing, the earthing has the capability to neutralize that object, the charged object, and keep itself discharged at the same time. It means it can give out or accept a small bit of electrons without even changing its property much. One of the physical example that it can be, that is very beautifully comparable to this thing, is that if you have let's say a bucket of water, and you drip your finger in the bucket of water and you pull it out, you'll see that the surface of your finger has become wet. But the amount of water that you are pulling out by means of surface added by the surface water of your finger, would that reduction of water practically cause any height drop of the water level of the bucket? Practically
No, sir.
No, sir.
This is not going to work out. So in this case we can say that no matter how many times of dip finger of water we take out from the bucket is going to still maintain its water amount. We can say this roughly. I mean, precisely speaking, it is not true. We are all definitely taking out water. So if you take, let's say, 1 million drops of finger drops, the water level will definitely drop down. But for a small number of cases, that we can pretty much consider that the water bucket level would maintain its water level. So an earthing object can be considered to be something like that. That whether we take some electrons out of it or we feed it some electrons, the number of electrons and electrons and protons would be pretty much equal. If you try to think about in terms of numbers, let's say an earthing object has 1 billion protons and 1 billion neutrons. To discharge an object, let's say you just supplied 100 electrons within that object. So now it has 1 billion 100 electrons and you have 1 billion protons. The difference is minuscule. You can pretty much say the object still pretty much has same number of electrons and protons. Minutely it doesn't, but overall it does. Do you understand the meaning of the word earthing? I mean, does the concept make sense? বুঝাচ্ছে কি?
Yes,
Sir,
sir.
could you explain again?
An earthing is an object which has such a huge reservoir of positive and negative charges that a small bit of addition of electrons or a small bit of subtraction of electrons does not practically make it charged. It always stays neutral and has the capability to make other charged objects neutral when it's get connected to them electrically.
Thank you, sir.
বুঝছো কি?
Yes, sir.
আচ্ছা, শাফাত রাজিন তোমার সাথে কত জুমায় দেখা হয়েছিল?
Yes, sir.
আচ্ছা, তুমি হচ্ছে আরিফের কাজিন।
হ্যাঁ।
আরিফ ভালো আছে?
Yes, sir. Or last session এটা।
দেশে?
পার্টিতে লাস্ট ইয়ার এই ইয়ার।
এখন কি দেশে?
না, এখন আমেরিকান।
আচ্ছা, যাক, ভালো, গুড। আচ্ছা, সো যেটা বলছেন, দিস ইজ দ্য কনসেপ্ট অফ আর্থিং। আর্থিং ক্যান প্রুভ এ ভেরি হেল্পফুল রোল ইন স্ট্যাটিস্টিক্স চ্যাপ্টার। ওকে, বালিশ দিয়েছো? পড়ে যাও না তো? এক মিনিট, পড়ান। Alright. So, okay, Asif asked me a question. So does earthing object have a charge? Well, that's a pretty interesting question. Asif asked me a question. So does any earthing object have a charge? Well, here's the deal. If you have any object that is neutral, in minute case, it does have charge, but it has equal number of positive and negative charge, which ultimately makes it neutral. Try to understand. Any object that is neutral does not have any overall charge, but it does have positively charged electrons and positively charged protons and negatively charged electrons. So it does have charged particles within itself, but being the number equal, you have an overall zero charge. So if you ask me, does the earthing object have a charge? Its overall charge is zero, but it is consisted of negatively charged electrons and positively charged protons, which happens to be an equal number. That's how I would answer this question. Asif, বুঝছো?
Yes, sir.
Okay. So the next thing that I go for is processes of charging or charging processes. আচ্ছা, তোমরা তো ইনসুলেটর ম্যাটেরিয়াল আর কন্ডাক্টর এন্ড ইনসুলেটর ম্যাটেরিয়ালের এক্সাম্পল দিতে পারো না? পারো কি? আচ্ছা, না পারলে আমি বলতেছি। Materials which are good conductor of electricity are called conductors, which are poor conductor of electricity are called insulators. Anything that logically has free electrons or moving ions within them, they can actually do good conduction of electricity. So in that sense, all metals, including mercury, graphite, which is an exceptional form of carbon, and also all sorts of electrolytic solutions, because they have moving ions. They have dislocated ions which can move apart to create electricity. So these are the basic three types: all metals, graphite, and uh, electrolytic solution, or salt water solution. In terms of salt and water solution, they all are good conductors of electricity. On the other hand, objects which do not have free electrons, they are considered to be poor conductors of electricity. They are considered to be insulators or poor conductors. For example, glass, plastic, wood, hair, human beings, etc. Now you might wonder, human beings are not good conductors of electricity. No, we are not good conductors of electricity in generally, but we can be made into good conductors of electricity by means of a high voltage. What that essentially mean, we're going to talk about in the practical electricity chapter, where we discuss detail about the process of getting a shock. How does a person get a shock and how to avoid that? Anyway, so these are differences, or these are some examples. You just have to know them and be able to write them if the exam ever asks you, or they might actually give you an MCQ question that which of these following objects are insulators. So they could give you some 4 or 5 words in one option choice. You have to read all of them and be able to choose which of the list has all the insulators and be able to tick that out. Something like that. Pretty easy process and rewarding question. In charging process, we basically have two charging processes. We have charging by friction and we have charging by induction. Friction is mostly for insulator materials. Mostly. I'm using the word mostly because I'm going to explain to you why friction wouldn't be a good idea for metals. And induction is mostly for metals. I'll tell you individually that why one of these processes, I mean, why friction is not a good idea for metals and why induction is not a good idea for insulators. I'll tell you that in a bit. First, how does friction by charging by friction works? What you need to understand that every atom has some attraction to every electron has some attraction with its atom. The amount of attraction can vary from electron to electron and from different one atom to another atom, but normally they're attached. They have some attraction to the atom. If I go into a bit more detailed discussion, you could তোমাদের সবার chemistry আছে না? All of you have chemistry, right?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so you do know what the periodic table is.
Yes, sir.
Yeah.
So you do know what group 1, group 2, group 3 these mean.
Yes.
Yes, sir.
Beautiful. So in group 1, the elements are arranged in such a way that they have one free electron in the outermost shell layer, and to have a stable octet or duet, is it called duet, double, what is okay, I forgot. But to have a stable octet layer on the outer shell layer, these group 1 elements are very willing to give up their one outer shell layer electron. So they will give up that electron very easily, even for without, I mean, using the stored heat energy within themselves. They would be able to dislodge, get rid of that electron and make themselves +1 charged and be happy about it, because they want to have octet on the outer shell layer. But interestingly, you cannot strip out one more electron from these ions. Sodium atom will give one electron without any effort and become Na+, but you cannot make Na2+. Not going to happen. Similarly, all the group 2 elements are going to give out 2 electrons pretty easily. First ionization is a bit less and second ionization is a bit more, slightly more, because of the charge differences, but they will not give out a third electron. That's going to be not happening. Why am I telling you this? I'm trying to give you an idea that the energy by which any electron is attached with the atom can have significant value differences. The one electron, the outer shell electron of the group 1 elements are very loosely attached to the atom, so they can get rid of everything. But one below, it means, let's say the octet shell layer and all the electrons underneath that level, they are all very strongly attached with the atom. I mean, even if you talk about like all the way up to the bottom, like sodium, potassium, lithium, sodium, potassium, rubidium, cesium, francium. These are the group 1 elements. So even if you go all the way down, they have a pretty large atom, like 281, 2881, 28, 1881. So it goes on like that. But even so, even at the very last one, francium, this is going to also give out one electron pretty easily, but it's still not going to give out one electron out of its octet shell. even if that shell is pretty far away from the nucleus, but it's still going to hold on to those electrons very, very strongly. Why am I telling all this? To give you an idea that the energy by which an electron is attached to the atom can vary from electron to electron and element to element. This is a very important point, because metals are those which has some electrons in their outer shell layer bonded with them with such a small amount of energy that they can readily give up those electrons, making a huge number of free electrons available in the crystal lattice. So if you have a block of metal, depending upon its periodic place, periodic table place, it can give out 1 electron group 1 elements, 2 electrons group 2 elements, 3 electrons group 3 elements, so on and so forth, which makes an abundance of free electrons within the whole block, and all the atoms become positively charged, and they produce the core, which is like the inside of the whole metal piece. And all the free electrons produce a very thin but very strong layer on the surface of the whole block, and they get attracted towards the core because of the positive charges. So continuously, always, that thin layer of electrons, it's a thin layer but it's a very strong layer. So that thin layer of electron is always squashing and squeezing and compressing onto the positive metal core ions. And that compressive force is essentially what gives metal the strength that it has. And one of the reasons aluminum is a very light and strong metal at the same time, because it gives out 3 electrons. Each of the atom gives out 3 electrons in the lattice, which is amazing. I mean, it has so many free electrons, and the squeezing force is so much that even though it's a pretty light metal, it can give us enormous amount of strength because the embedded electron numbers is so high. Aluminum also happens to be one of the very good conductors of electricity as well. বুঝছো কি বলছি বলবান?
Yes,
Yes,
sir.
sir.
Yes, sir.
All right. So metals দের প্রপার্টি হচ্ছে, মেটালস এর মধ্যে এরকম লুজলি অ্যাটাচ ইলেকট্রন থাকে, সেগুলো ইজিলি বের হতে পারে, এবং সেগুলো বের হলে সে মেটালগুলো কন্ডাক্টিং করে। আর ইনসুলেটর ম্যাটেরিয়ালের ইলেকট্রনগুলো তাদের সাথে খুব স্ট্রংলি অ্যাটাচ থাকে। The outer shell electrons and all the other electrons as well, they are really strongly attached within the chemical bond that the insulator materials build. For example, if you think about wood, they make large polymeric chain with strong covalent bonds, so all the electrons are stuck within the covalent bond, so there is no reason they're going to come out and do conduction. The electrons are all the electrons are strongly attached, pretty much like you have to think that the second electron from the sodium atom is not going to come out. It is attached very strongly with the atom. In a similar manner, for covalent bonds, the electrons are also very, very strongly attached. So that's why we have to introduce friction for the insulator materials. Now, let me tell you how does the friction work. Let me just draw you a figure, and that might actually help you understand this thing better. Let's say this is a insulator atom, and let's say this insulator atom has one outer shell electron over it. It has a lot of other electrons as well. I'm just drawing one. Let's say this electron is attached with the atom with an energy of 10 joule. This figure is highly unlikely. We are assuming this just to make conversation. If I say that this electron is attached with the atom with 10 joule, it means that if I want to strip this electron, if I want to remove this electron from this atom, I have to energize this electron, exclusively this electron, by 10 joule, not the whole atom. This electron itself should absorb somehow an amount of energy which is 10 joule, and that's when it can overcome the attraction of the atom and eventually become out of the atom and become free. We can do that. Now, how could we possibly supply this amount of energy to this insulator atom is another question. That's precisely where the friction comes in. The idea is that if we have a rod or cylindrical object of insulator material, and if we take a cloth of another insulator material, we're taking a cloth because a cloth is a flexible thing. We can very easily wrap it around and do good contact surface. If you don't have a cloth, we also can take another rod which is made up of a different material, and we can also rub them side by side. But the problem is that in that case, your contact surface would be very small because you have two cylindrical objects, so you're definitely going to have less contact area. So we are only preferring to have one rod and one cloth to increase the surface area, to increase the contact locations as we are going to rub. So let's just forget about this thing. And these two substances naturally will have two different values of attaching energy. For example, let's say this rod, the outer shell layer of this electron requires 10 joule each to become free, whereas the electrons of this one requires 15 joule each, which means these electrons are more strongly attached and these electrons are less strongly attached. Now what we're going to do, we're going to bring them closer and we're going to start rubbing them. By rubbing, we're going to convert the work that we're doing by means of friction into heat energy. This heat energy will be given to the outer shell layer electron of both of these objects, for the cloth and also for the rod. Now here's the thing, as the temperature of the contact surfaces increase for both of them, which electrons are likely to have the required energy to be free up earlier? Should these electrons have enough energy earlier, or should these electrons have enough energy earlier? I'll ask the question again. We are rubbing both of them, so we are generating heat. Temperature is increasing, which temperature is getting absorbed by the outer shell electrons of this object and also for these inner objects, for the contact surface. As the temperature goes higher, the individual energy stored in the electrons also becomes higher. My question is, between these two objects, which electrons will be able to get their liberating energy or their bonded energy amount earlier? Should these get earlier or should these get earlier?
10 Joule one.
10 joule one.
Logically, 10 joule particles would get their required amount of energy earlier because that's a lower amount and 15 joule is a higher amount. So what's going to happen as we will keep on running, you have to understand that energy would be given to both of them because we are rubbing and heating up both of these objects. But as the temperature will keep on increasing, these particles will have their liberating energy earlier compared to these particles. So electrons are going to start to leave from this object and electrons are going to getting absorbed within this object. So in this process, this cloth is going to become negatively charged and this rod is going to become negatively charged. Does this make sense?
Yes,
স্যার
sir.
আবার একটু বলবেন?
Because this object's electron has a lower liberation energy. I'm using the term liberation energy, it's not actually physics term, I'm trying to make sense with you, so don't write this term, try to understand. Because these electrons have a lower liberation energy compared to these particles, so as we keep on rubbing and the temperature of the surface increases, these electrons are going to have the required amount of energy earlier compared to the electrons of this one. So some of these electrons which actually can manage to have 10 joule energy of their own possession, they're gonna free themselves up from the surface and eventually they're going to enter into the cloth. That's going to happen. So because electrons will be leaving from the rod and entering into the cloth, this would lead to, after a certain amount of rubbing, this will lead to the incident that the rod is going to become positively charged and the cloth is going to become negatively charged. For these two pairs, let's say this is glass and silk, because this actually happens, I mean glass and silk. If we do rub this together, we are going to have this one becoming positively charged after the rubbing process and this one will become negatively charged after the rubbing process. বুঝে গেছে?
Yes, sir.
আচ্ছা, if it were the other way around, if the solid or cylindrical object had more attraction or had the electrons value to be higher, then it would be also possible that the cloth could become positively charged and the rod could be negatively charged. So which object has more attraction towards electron? There is a certain list made out of this thing. Scientists made this thing. This is called triboelectric series. Triboelectric series. You can look it up in your Google. It is not a part of your syllabus, but if you're just interested, there is a huge listing of objects. And if you rub any of the top one with the bottom one, one of them is going to become, I think the top ones are going to become positively charged and the lower ones are going to become negatively charged. That's how this list is made. So the top ones are positive and the lower ones are negative. But I actually not sure. But if you want to look it up, you can look it up in Google and you can find out that list. That's basically the idea of charging by friction. I'm going to finish this up and then we're going to take the pair break. The reason charging by friction works for nonmetals is that nonmetals do not carry electrons from one side to another side. Whenever we are rubbing, the moment one electron gets free from the surface, it will not travel to other places. It will immediately get absorbed by one of the atoms which was very adjacent to this thing. So you're continuously rubbing, the electrons is absorbing energy and it is getting energy. The moment it actually can manage 10 joule of energy, it will immediately free itself up and get absorbed into the cloth. And that electron, the location where this electron is getting attached, it will pretty much stay over here as well. It's not going to flow through the entire cloth because the cloth is also made up of insulator. We are rubbing two insulators over here. So the electron transfer is happening from one atom to another atom. That's it. It is not actually traveling through the object because they are both insulators. This is why if we keep on rubbing them, we can slowly make them more and more charged. They are not going to flow naturally by metals and eventually discharge them each other, because that's not how they work. Each individual atom losing one electron will become positively charged. Each individual atom over here accepting an electron will become negatively charged. Now, if you wonder, is it possible for them to become plus 2e? Well, ideally, if the first energy is 10 joule, the second ionization energy might as well be, let's say, pretty high. So unless a significant number of neutral atom becomes plus 1 charge, the possibility for happening plus 2 is actually quite low, like really, really low. Or that might actually happen or start to happen if we keep them rubbing for a really long time. But that will also be a very difficult thing to achieve, because the longer duration that we're going to rub them together, this is going to become more and more positively charged, this is going to become more and more negatively charged, which means by virtue this is going to start to hold on to its electrons more strongly, and this is going to start to repel further incoming electrons, because like charges attract and opposite charges repel, like charges repel and opposite charges attract. So the more positive charge it becomes, it would be unwilling to lose more electrons, and the more negative charge it becomes, it would be unwilling to accept more electrons. Do you understand my point?
Yes, sir.
এই পর্যন্ত বুঝে গেছে কিনা সবার?
Yes, sir.
আচ্ছা, it's 6:28. We're gonna take a prayer break. I'm gonna pause the recording and we're gonna resume class in, let's say, 10 minutes. So 6:40. Resume recording. Yes. So what is happening here? That was the case for charging by friction. Now, one thing is very important. Important part একটু পরে বলতেছি. Let's discuss charging by induction. Induction জিনিসটার basic আইডিয়াটা আগে বলি, তারপর আমি charging by induction বলতেছি. Induction basically means to change the property of an object temporarily by the presence of something else nearby. I'll say it again. Induction essentially means to change the property of something temporarily by means of presence of something else nearby. This is what induction normally means. Charging by induction basically is applicable for metals. The process works in a very simple way. Let's say we have a metal sphere which is placed upon an insulator stand. This is important. The stand has to be made up of insulator so that it cannot be discharged through the stand, and this is metal, so I might as well draw that with ash color maybe. So this is the metal piece, and let's say currently the metal is neutral, which means it has equal number of positive and negative charges, equal number of protons and electrons. If we bring a previously charged positive object close to it, let's say we have a positively charged glass rod which we could obtain from this process, and if we bring it close to it, we are not even touching, we're bringing it only close. So this is a positively charged rod. Because of the presence of these positive charges, the electrons of this metal sphere are going to get attracted to this thing. All electrons will be attracted, but all electrons cannot move. Only the delocalized electrons or the free electrons can move. And all of the free electrons will be attracted, but all of the free electrons cannot come over here. Some electrons will be able to come over here, because as more and more electrons will be reaching to the right side, let me label them with green, they will repel the incoming of further electrons. So there is a default natural equilibrium that, let's say, here I have drawn 4 electrons over here, which is going to leave 4 positive charges on the other end. You have to understand that for this thing to happen, electrons move this way. Positive charges did not move, because electrons left from the left side and moved to the right. That's why the right side has become temporarily negatively charged and the left side has become temporarily positively charged. This state of charge division is what we are defining as induction. This is a temporary state. It means if we now remove this object altogether, if we take this object away from this thing, then this object will once again become perfectly neutral. These electrons are going to redistribute themselves or across the whole thing, or they will be evenly distributed, and as a result the whole metal sphere will once again become perfectly neutral. That's why we are saying this state is temporary. It is not permanent. The idea of induction. So we are making a bit of a charge separation, or we are separating opposite charges temporarily. We call these charges fixed charges. We call them fixed charge because they are going to be stuck over here by means of the attraction of this positively charged rod. Whereas these charges which are on the other side, we call them free charges. Free charges means that they are going to be produced on the farthest possible end of the fixed charges, and they can be neutralized. Fixed charges cannot be neutralized, cannot be neutralized because they are stuck over here. I'll show you what happens for the opposite case as well, so don't bother. And free charges can be neutralized, can be different words, so can be neutralized. So if we now provide an earthing connection to our earth connection to the with this metal sphere, anywhere in the anywhere on the sphere, you can even you also want you can also connect it right on this side. We can connect it over here, or we can use one of our fingers. Let's say if I draw a finger, we can draw a finger with a nail, pretty bulky finger, and nail polish nail or whatever. So if we have a finger, and if we touch the finger anywhere on the sphere, anywhere, and it can be even on this side, it can be on this side, it can be over here, anywhere, providing an earth connection anywhere on the sphere is only going to neutralize these charges, not these charges. That's the important bit. So so you can see that this here we have some positive charges. If you want to neutralize them, what do we have to do? We have to feed some negative charges here, which means if we do connect an earth connection over here, let's say I'm going to draw an earth connection from here. This is the circuit symbol for earthing, 3 parallel lines slowly decreasing in size. This is the earth connection for circuit symbol for earth connection. If you provide an earth connection, in this case, electrons are going to rise from the earth and go into here. In this case, 4 electrons are going to go up there and eventually neutralize this part. And as a result, we're going to have from here, we're going to have the same metal sphere standing on the insulated rod, and the positively charged object is still here producing its induction 1 2 3 4 5 6 7 1 2 3 4 5 6 7. I'm trying to keep the figures logical, and we still have the fixed charges are still here, but the left side has become discharged, and the earthing connection is still connected, let's say. Now what is important at this point, there is a very important thing that you should understand. If we want to keep these negative charges stuck within the metal sphere, we have to first disconnect the earthing so that these electrons cannot escape to the earth, and then we have to remove this. So first this has to be disconnected. So if I erase this over here, so we have disconnected the earth connection. Now the electrons cannot escape, and now if we I cannot rub this, not the whole thing. Okay, I have to select and delete it. And now if we remove this thing, then we do not have any more inducing objects. So in that case, all the negative charges are going to redistribute themselves evenly across the whole sphere, and we might as well have the 4 negative charges separated out as far as they can, and all the sphere will become negatively charged. But the number of charges would remain the same. We had 4 negative minus signs over here. We should also show 4 minus signs over here. Important bit: the earth connection has to be removed first so that the electrons cannot escape, and then the inducing object should be removed so that the produced charge within the metal can be stored, or it will be stuck within the metallic sphere. So that's how charging by induction works. If it is a reverse thing, for example, if this object was negatively charged, let's say if we had a metal sphere which was neutral in the to begin with, and let's say once again metal sphere standing on an insulator stand, and if we bring a negatively charged rod over here, if you wonder why do we get the negative charge rod, in the same process over here, only in this case we have to choose 2 different materials. I'm going to tell you 4 different materials, and an easy way to remember them. If you bring a negative charge rod over here, in that case, the way we describe that, these negative charges of the rod are going to repel the electrons of the metal sphere, and some electrons are going to be shifted to the far side. Let's say I'm once again giving 4, and the closer side will become positively charged. This sphere by logic is still very much neutral, but because of the presence of this negatively charged rod, we have a separation of charges, which is the basic essence of induction process. And once again, if we do provide an earth connection, in this case the far charge or the free charge will become neutralized. In this case, electrons are going to move back to the ground, making this side perfectly neutral. And then to make sure that the positive charge stays within, we have to disconnect the earth connection first. So let's say we disconnect the earth connection, and then if we remove this thing altogether, these positive charges are going to distribute themselves all over the sphere. Now there is a catch. This sentence that I said is not essentially correct. I'll say it again. These positive charges will redistribute themselves across the entire sphere evenly. Do you think this sentence can be correct? I'll say the sentence again slowly. I want all of you to judge. These positive charges will now redistribute themselves across the entire sphere. Is this statement correct or not?
Yes.
It is possible, sir, like with enough spacing.
Okay. Hear me out on this one. I told you at the very beginning, positive charge is only created by which particles? Protons. Can protons move?
No, sir.
So when I say this, these positive charges will redistribute themselves across the whole sphere, is this sentence perfectly correct?
No, sir.
In essence, it is logical. If you write this at your O levels, you will still gonna get marked. But I appreciate a different version of this. I prefer students should never write about positive charges, like never. Whenever movement is involved, you should never write about positive charges. Whenever movement of charges is involved, you should always write about electrons. What I would appreciate to explain for this upcoming sentence is that the remaining electrons in this metal sphere are going to redistribute themselves such that there is even positive charge all over the sphere. Hear me out once again. The remaining electrons in the metal sphere will redistribute themselves so that there is even positive charge all over the sphere. So who are going to move? Who are going to redistribute themselves? Not the positive charge, because the particles which can move are which?
Electrons.
Electrons. So I'm using the word, to be careful, I'm using the word remaining, because in my example I just showed you a bit earlier that electrons moved out of the sphere. So the remaining electrons, which are shorter in number compared to the number of protons that we have within the sphere, so the remaining electrons will redistribute themselves across the sphere so that the positive charge is evenly distributed. And that's how we can charge a metallic object by means of positive charge. In this case,
So what if all of the electrons were earthed?
Well, here's the thing. We can almost never remove all of the electrons. I mean, if you ever write all of the electrons, things are gonna become extremely, what can I say, complicated to grasp. I mean, writing all of the electrons might actually mean, in terms of grammar, all the electrons, not necessarily all the free electrons. I mean, that's not gonna happen, right?
No, sir.
Because that would require the entire structure of atom to be destroyed, and all the protons and neutrons, all the nucleus on the positive side, and all the electrons, shell electrons and outer shell electrons, everyone has left. So writing all the electrons is a very wrong thing. That's problem number one. You should not write that. That's wrong. If you write all the free electrons are gonna be neutralized, would that be correct? That is also a no. I'll tell you why. We have a certain amount of positive charge on this rod. How much induction can we make by the presence of this positively charged rod onto this thing, or how much positive charge could we make over here by means of the earlier drawn negatively charged rod on over here, is highly dependent on two factors. How much charge does this object have in the first place, and how close are we bringing them? Now we cannot bring them really close, because if you bring them really close, there is a possible of contact. We don't want to make contact. We only want to make induction, which means we're going to bring them close, and we're going to induce the property that is dictated upon the metal sphere because of the presence of this other rod. So, and whenever you are making charge separation, I have to understand one thing. সেটা হচ্ছে কি রকম যে মনে করো এই রডটা এখন মনে করো অনেক দূরে আছে, আমি এই জিনিসটাকে কপি করে নিই। কপি করে নিলে বুঝাতে একটু আচ্ছা কপি না, আমি এখানে আঁকলেই বুঝতে পারবো সহজে। মনে করো এটা হচ্ছে আমাদের নিউট্রাল মেটাল স্ফিয়ার on an insulator stand, and মনে করো এখানে হচ্ছে আমাদের পজিটিভলি চার্জ রড। মনে করো হচ্ছে এই ডিসটেন্সটা হচ্ছে অতটুকু বেশি। লেটস সে the distance over here is so large that here we have no induction. The way it works, if I start to bring it slowly closing in that case, slowly we're going to produce more negative charges over here. So if the object is over here, we're gonna so yeah, if it's over here, let's say there was no charge. Let's say whenever we bring it over here, we might as well have 1 minus sign, 1 minus sign and 1 plus sign. If you bring it even a bit more, if you bring it slightly closer, we're going to make more induction. So in that case, you're going to have one more minus sign and one more plus sign. So the farther you bring it close, you're going to make the induction process more strong. And you can never actually separate out all the electrons, because as this side becomes more negatively charged, this will tend not to allow the incoming of more electrons, because like charges repel. Similarly, as this side becomes more positively charged, this will be less willing to give out more electrons, right?
Yes, sir.
মানে একটা নেগেটিভলি একটা অলরেডি নেগেটিভ সাইডের ভিতর ইলেকট্রন ঢুকানোটা ডিফিকাল্ট, একটা অলরেডি পজিটিভ সাইড থেকে ইলেকট্রন বের করা আরো ডিফিকাল্ট। এন্ড পজিটিভ সাইডটা যদি দুইটা প্রোটন দিকে হয় তাহলে যতটুকু ডিফিকাল্ট হবে, যদি তিনটা প্রোটন থেকে হয় তাহলে আরো ডিফিকাল্ট হবে, যদি চারটা প্রোটন থেকে হয় তাহলে আরো ডিফিকাল্ট হবে। তার মানে তুমি যত বেশি ইন্ডাকশন করতে থাকবা, তোমার ফার্দার ইন্ডাকশন প্রসেসটা এসেনশিয়ালি আরো বেশি এনার্জি ডিমান্ডিং হবে, ঠিক না?
Yes, sir.
তার মানে হচ্ছে প্র্যাকটিক্যালি স্পিকিং আমরা কখনোই একটা অবজেক্টের সবগুলো ফ্রি ইলেকট্রনকে ইন্ডিউস করতে পারবো না। আমরা কিছু সার্টেন নাম্বার অফ ইলেকট্রনকে ইন্ডিউস করতে পারবো, বাট ইটস নেভার পসিবল টু মেক এন ইন্ডাকশন অন অল দ্য ফ্রি ইলেকট্রনস। দ্যাটস নট গোনা হ্যাপেন, because it is an ever increasing requirement of energy that is required to actually make more and more induction process. Did I answer your question?
Yes, sir.
Achha. Any further question about the whole process of charging and discharging for metals and non-metals? বুঝে গেছে সবার?
জি স্যার।
অলরাইট, ইম্পর্টেন্ট একটা জিনিস যেটা বলতে চাইছিলাম সেটা হচ্ছে এখানে আচ্ছা দুটো ইম্পর্টেন্ট জিনিস বলি। একটা হচ্ছে তোমাদের দুইটা পেয়ার ম্যাটেরিয়ালের নাম্বার, ইউ হ্যাভ টু রিমেম্বার দ্য নেম অফ টু পেয়ার ম্যাটেরিয়ালস হুইচ বাই রাবিং ক্যান গিভ আস টু অপোজিট টাইপ অফ চার্জেস। This is how I usually teach the students, is that remember this alphabet sequence E, F, G, and then not H but S, which sounds like a bit like H but it is actually S. So if you remember these four letters, you can have a good it will be easier, and pair them in two and give minus sign on outer sides and positive signs on the inside. Now this is the part that you might forget, that well, why? You just have to remember that the positive and negative amounts, you can also remember by the structure of atom. But however, if you remember this much, this is a good thing. This actually helps to remember us two things. This pair stands for ebonite and far. Ebonite is a very special type of insulator material. It is mostly used in the circuit board, in the switchboards. In the switchboard, ebonite is a type of polymeric plastic which is highly heat resistant and also burn proof. Burn proof means that typically electrical sockets and electrical switches and electrical boards are typically made from ebonite, because ebonite is such a material that if they are highly heat resistant, it means they have a very high melting point, and even when they are melting, they will not catch fire. They are flame resistance or burn proof. You'll see them actually melt, or you might actually be able to do them oxidization, but there would not be produced a flame. So no matter how much heat you give, they will not catch fire. So ebonite is that kind of material. You don't have to know the purpose of ebonite. I'm just giving you a bit of a reference so that you can relate it to with your regular life. And fur means fur of any animal, fur, cat fur, dog fur, not human fur, fur. So if you rub a rod of ebonite with fur, ebonite rod is going to become negatively charged and fur is going to become positively charged. And then this is for glass and silk. If you have a rod of glass, you rub it with silk, then glass is going to become positively charged and silk is going to become negatively charged. You have to remember the name of these four things in pairs. Ebonite rod rubbed with fur gives you ebonite negative, fur positive. Glass rod rubbed with silk gives you glass positive and silk positive. Can you remember this?
Repeat this again.
Yes.
Repeat this again, the positive negative thing.
Oh, this is I mean, are you asking me why does this happen, or are you asking me which one is what?
Why does this happen?
Because in the triboelectric series, this is how they are arranged. I mean, if I look at the triboelectric series, let me just show you, because it's a good question. I can answer. Not needed for your syllabus, but it's a good question. So let me just show you. Okay, this is a big one. Can we read this? Triboelectric series. So here we have glass, which is the highest positive, and then we have silk. So if you rub glass with silk, you get glass positive and silk negative. I mean, if you wonder, I'm not getting into the itsy bitsy physics, minute physics or chemistry discussion. What I want you to understand that if you're rubbing glass with silk, silk has a more stronger attraction for electrons, and glass has a weaker attraction for electrons. So if you rub them for the same temperature, glass would be more likely to give up electrons compared to silk. So silk is gonna absorb those free electrons given up from the glass material. That's how it works. I mean, in this series, the materials which are above, they have weaker attraction towards electron compared to the ones which are lower. So the lower ones attract electrons strongly, the upper ones attract electrons weakly. That's the basic information of glass. বুঝছো?
জি স্যার।
So এখানে যে গ্লাস সিল্ক এখানে আছে, আর হচ্ছে আরেকটা জিনিস কি দেখলাম আমরা, এবোনাইট এন্ড ফার। ফার কোথায়? এই লিস্টে কি ফার আছে?
Yes sir, the first one.
Oh, far is here, and then polyamide. I think this is ebonite. No, ফারের নিচে থাকবে হচ্ছে ফার তো পজিটিভ হয়, ফার পজিটিভ, হ্যাঁ ফার পজিটিভ। সো ফারের নিচে থাকবে হচ্ছে এবোনাইট। দাঁড়াও আমি বলতেছি। Ebonite is a brand name for metal generally known as hard rubber. Is obtained by vulcanizing biology. Ebonite, maybe what is ebonite? What is ebonite meant? This is another one. This tend to electron lose electrons, this tend to gain electrons. So we have glass over here, silk over here, and ebonite over here, and far over here. So if you rub far with silk, you're gonna have far becoming positive, silk becoming negative. But the pair that we typically teach is the glass with silk and far with ebonite. I'm not telling you the exact reason why it works like that. I'm just telling you that that's how they behave. So I'm telling you the what part of the topic, not in detail the how part of the topic. This is not part of the syllabus. Samira, বুঝছো?
জি স্যার।
So that's one thing. The other thing that I'd like to take your attention to is this is a thinking exercise. So I want all of you to listen to this next part and try to respond to it. So I'll try to be slow. Let's say you have a positively charged glass rod that you so you have a neutral glass rod, then you rub it with silk, and silk cloth become negatively charged, and the glass rod has become positive. So you have a positive glass rod. In your opinion, what would be the most effective and functional and logically achieving way to actually neutralize this glass rod? How could you possibly neutralize this glass rod? If you want to neutralize this glass rod, what would be a possible way?
Second, repeat.
You have a insulator glass rod which is now positively charged. You want to make it back to neutral. How can you do that? It's very easy to neutralize a metal
Friction.
by friction. How?
Using a ferrite, a piece of cloth. Sorry, using a piece of cloth.
What cloth? What material? And even if you rub it with some cloth, do you ensure that this object at the end of your rubbing process will be neutral? Can you definitively assure that?
Sir, earthing.
No.
বুঝি নাই।
Earthing করলে হবে না?
Well, earthing কিভাবে করবা, মানে how do you propose to do that earthing? With a wire?
Can be.
Well, we definitely can, but that wouldn't be very effective because glass itself, by inherently or by its own property, it's not a good conductor of electricity. So even if we connect one earthing wire on one side, there is no reason the electrons are going to be able to pass through the glass material to reach up to the positive ions and utilize them individually, which is possible to achieve for a metal rod. And because metals are so good, and because metals are so easy to charge and discharge, it is also storing charge in a metal piece can also prove to be pretty difficult. I mean, if we have a charged metal piece, we have to be careful so that it doesn't lose charge because it tends to discharge pretty easily. But that's not the case for non-metals. Non-metals tend to store charge pretty easily. If you want to discharge these non-metals, in my opinion, what would be the way? We have to use some sort of earthing. Now think of a way of effectively using an earthing so that we can make this glass rod actually neutral. I'll help you to think. আমি একটা করে clue দিতেছি, and whenever any solution comes in your mind, please share it with us. You have to understand that each of the glass molecules which are now positively charged has lost, let's say, one electron each. To make the whole rod neutralize, we have to make sure that each of the glass molecule that did lose one electron, we have to deliver one electron to exactly that molecule, and has to happen for all the charged molecules exactly in that location. Now, essentially, we cannot see or define precisely which molecules did lose the electron. So we should be providing a free electron source to all the molecules, maybe, and so that whoever needs an electron can pick it up and others should not.
We bring a negatively charged rod to it.
বুঝি নাই?
Bring a negatively charged rod to the glass rod.
If we bring an negatively charged rod close to glass rod, we should have some sort of atomic level deformation. But how does that help? The glass rod doesn't have any moving
So
charge.
after that, there will be separation of separation of charges, right? So
No,
after that,
no. Here's the deal. Just a second. Asif, separation of charges happen where charges can flow. Separation of charges happen only in metals. In a non-metal or insulated material, you do not have separation of charges. If you have a glass rod and if you bring a previously charged rod close to it, nothing will happen within that rod. But if you have a metal rod, which is neutral, and you bring a charged object to go close to that, then you are going to have opposite charges produced. Did you get my point?
yes, I got it.
হ্যাঁ, আরেকটা কি যেন কথা বলছিলাম, সপ্তর্ষি, হ্যাঁ বলো।
হ্যাঁ স্যার, কোনো কিছুর সাথে রাব করে can we ensure যে the glass rod gets some negative charges due to friction?
Yes, so what could that thing be?
The silk.
But let's say you are rubbing a silk cloth with the glass. In that case, the silk is going to become more negatively charged, glass is going to become more positively charged. That would not be a good idea. Well, here's the thing. We just saw tubularity say, so glass is a human hand. So if we think that we are going to rub a human hand over the glass rod, then human hand should be giving up electrons and the glass rod should be accepting electrons. But the question is, when do we understand that this glass rod has perfectly become zero? I mean, if you keep on rubbing for a longer duration, it might also happen that the human rod, the hand becomes positively charged and the glass rod becomes negatively charged, because in the tubularity series, human hand is above. So if you rub them together long enough, the glass rod can become neutralized and eventually start to become negatively charged. We don't want that to happen. I asked you the question that if you want to definitively make sure that the glass rod is perfectly neutralized, what should we do? Do you understand my problem?
Yes sir.
Well, here's the deal. A human hand, rubbing with a human hand can actually work. I'll tell you why this would work. I'll tell you about the human hand first, and then I'm going to give you the actual methodical solution, which is usually recommended for lab processes. সেটা হচ্ছে, our body, a human body, can also work as an earthing. You might wonder how. For small case charge transfer, our body can work as an earthing because our body has a huge stockpile of ionic solution. It's called blood. So we have a huge stockpile of positive and negative ions within our bloodstream. So we can actually take a little bit of electrons, or we can give up a little bit of electrons. Even so, our body's effective voltage can still be 0 volt, or we can still be effectively neutral. So our body can work as a small source of earthing, but not for large electrical sources. For small static electricity experiments, our body can work for that. So if a person is, let's say, standing bare feet on ground, if a person standing bare feet on ground and they take their hands and rub the glass rod well, we can pretty much expect that, and at the end of the rubbing process, no matter how long, both the glass rod and the person will be perfectly neutral. The reason is that we are making the person stand bare feet on the ground, which means the electrons, if they want, they can actually be grounded to the person's body. And because we are rubbing it with our hand, so whenever the electrons will be penetrating our skin and eventually entering the bloodstream, the electrons can actually leave from the bulbosity. Whenever the electrons can leave our skin and from the bloodstream, they can enter into the glass rod's individual molecules, and as a result, they can actually make them neutral. This, in theory, should work. But a much more better or effective thing can be achieved in a different way. You guys have seen the steel wool that we use to rub the cookwares after cooking. Have you guys seen that? ওই যে স্টিলের একটা মাজনি আছে যেটা,
To wash the dishes.
yeah, to wash the dishes, especially to remove the
Yes.
burns.
Yes.
Do you guys know what I'm talking about?
Yes, sir.
Basic majuni. We can take a thing like that, or a steel wool lamp, and have one end of the steel wool connected with an actual earth connection, a wire that is connected with the earth connection, and then rub the steel wool around this glass rod for maybe 5 to 10 seconds or so. We have to make sure that we wrap the steel wool around the glass rod and make a good rub across all of them. The idea is, because steel wool itself is a good conductor and it is connected to earth, any single time any end of the steel wool comes in contact with any of these positively charged atoms, the atom will immediately pull up one electron from the steel wool, because steel wool has a huge reservoir of electrons. It's metal, right? So steel wool doesn't have any problem giving up electrons, because it has a lot of free electrons at every end of it. And at the same time, it can pull up extra electrons because you have provided an earth connection with the steel wool. So the idea is very simple. Let's say this is a steel wool, and you take an earth connection to this one, hold it by your hand. Maybe you might choose to wear a glove, or you might choose not to wear a glove. It really doesn't matter. But let's say you're wearing gloves, because in this case we are trying to talk about that electron transfer through this material, and then wrap it around and give it a bit of good rub on all sides. What will happen now? You can pretty much make sure that all the positive charge atoms did get their supply of individual electrons, and the entire glass rod can be actually neutral. This can be achieved by a very small duration of rubbing, but if you are willing to rub it for even long duration of time, let's say if you want to rub it for, let's say, 10, 15, 1 hour, even so, at the end of that process, your glass rod would still be discharged, because we have this steel wool connected with what? With ground. বুঝা যাচ্ছে কি বলছি?
Yes, sir.
সবাই
So
যদি-
the human hand is giving the electrons to the wire, and the wire is giving it to the rod.
Well, if we do not connect it to the if we do not connect it to the ground, let's say if we only hold it by our human hand, let's say here is a human hand holding this steel wool. In that case, the human body is working as the actual ground. Human body is the ground, which is providing the steel wool enough supply of free electrons. And because the steel wool has a lot of free electrons available by default available within its metallic bond, it can give out 1 electrons to each of these positive charge atoms very easily. So you're basically offering electrons to everyone, so whoever needs it can pick it. But you're not pushing the electron to everyone. You're making a free choice to pick up an electron to all the atoms of the glass rod, and the ones who require it are going to take it from the steel wool. That's the idea. বুঝতে পারছি?
Yes, sir.
বাকি সবাই ক্লিয়ার হয়েছে কিনা?
জি স্যার।
Okay. So এটা গেল. This is and in this case, whenever the neutralization will work, electrons are going to flow from the steel wool into the glass rod, and that's how the electrons are going to move, because we are trying to neutralize some positive charges. And if it was the other way around, it would just happen the other way around, but the method would be exactly the same. If it was a negative charge rod, electrons would flow from the rod into the steel wool and to the earth. But the physical requirement, the components that you're going to require to make sure that an object is perfectly neutralized is pretty much the same. The next part that we have in our static electricity chapter is what we call field, electric field and electric field lines. So let's go for that. Field lines was primarily introduced by, I think, Michael Faraday. Yes, Michael Faraday. Michael Faraday was the first person to introduce field lines to us human beings. I mean, although it's said to be sort of like a bit of a fun or sort of a slightly joke towards Michael Faraday, but it was said that Michael Faraday was not very good at visualizing or representing the strength of magnetic field lines or a certain field. So he used lines to represent a field. This initially was a pretty weird idea when he first introduced it, but over time, this method of representing a field using lines proved to be very effective and simple to draw and manipulate as well. So the idea is that, what do we understand by field? A field is essentially a region of space. It doesn't mean it's a plane. It means a three-dimensional space. A field essentially means a region of space within which some force can be experienced. Now, I'm using the term some force because I'm giving you a holistic definition of field. If it's a gravitational field, then you have to say it like this, that what is a gravitational field? A gravitational field around an object is such a space, region of space, within which another object with mass can experience the gravitational force. What is an electric field? An electric field around a charged object is the region of space within which another charged object can experience an electrical force. What is a magnetic field? A magnetic field is a region of space around a magnet within which another magnet or another magnetic material can experience a magnetic force. So একটা certain region of space যতটুকুর মধ্যে একটা pre-existing object থাকার কারণে অন্য একটা অবজেক্ট একটা সার্টেন ফোর্স এক্সপেরিয়েন্স করবে। আমি তিনটা ফোর্সের কথা বলছি, গ্র্যাভিটেশনাল ফোর্সের কথা বলছি, সে গেছে গ্র্যাভিটেশনাল ফিল্ড, ইলেকট্রিক ফোর্সের কথা বলছি, সে গেছে ইলেকট্রিক ফিল্ড, ম্যাগনেটিক ফোর্সের কথা বলছি, সে গেছে ম্যাগনেটিক ফিল্ড। সো ফোর্স এক্সপেরিয়েন্স করার যে স্পেসটুকু একটা প্রি এক্সিস্টিং অবজেক্টের জন্য, ওই স্পেসটুকুকে আমরা বলি হচ্ছে ওই অবজেক্টের ফিল্ড। ফিল্ডের বেসিক্যালি এটা বুঝে গেছে? যেমন আমি যদি ফিজিক্যাল একটা এক্সাম্পল বলি, মনে করো হচ্ছে যে মাস্টারমাইন্ডে জিনাত মিস এখনো আছেন?
সরি স্যার,
মাস্টারমাইন্ডে জিনাত মিস এখনো আছেন?
হ্যাঁ স্যার।
উনি কি এখনো ফিল্ড ডিউটি দেন?
মোস্ট প্রবাবলি নট।
আচ্ছা, আমি যখন মাস্টারমাইন্ড ছিলাম তখন জিনাত মিস অনেক ফিল্ড ডিউটি দেন, সব বাচ্চারা খুব ভয় পাইতো। মানে এটা মনে তোমাদের বলছি না? আচ্ছা, যেটা হইতো, আচ্ছা আই এম গোনা ফিনিশ ইট প্রিটি ফাস্ট। যেটা হইতো সেটা হচ্ছে যে আমি তো ফিজিক্স ল্যাবে বসতাম, তো ফিজিক্স ল্যাব তো হচ্ছে বিল্ডিং এর পেছনের দিকে। তো ফিজিক্স ল্যাব কোথায় চিনো তো?
ইয়েস স্যার।
স্কুলে ফিজিক্স ল্যাবের উপরে ওই যে টিচারদের বসার একটা জায়গা আছে না,
জি স্যার।
সিঁড়ি দিয়ে, ওইখানটাতে আমরা সব টিচাররা বসতাম। তো যেটা হইতো যে ওই অফিস রুমের ওই দিক দিয়ে টিফিন পিরিয়ডের পর জিনাত মিস হাত দিতে ঢুকতেন, আর হচ্ছে তোমার ওই যে বন্যার জলের মতো সব পোলাপান এদিক দিয়ে এসে এই ইয়ার নিচ দিয়ে ওই কি বলে ক্লাস 10 এর সেকশনের নিচ দিয়ে, তারপর হচ্ছে ফিজ ল্যাবের নিচ দিয়ে, আর হচ্ছে ওইখানে ইয়া থাকে কি বলে ওই যে টেবিল টেনিস খেলার যে কোর্ট, ওই পার্ট দিয়ে এসে সব পোলাপান বিল্ডিং এ ঢুকে পড়তো। And this was a pretty common thing. যে জিনাত মিস বলতে ঢুকতেছে, পোলাপান সব মানে সুইপস অ্যারাউন্ড দ্য ফিল্ড। তো এখন ফিল্ডের এক্সাম্পলটা এই জন্য বলতেছি যে ওই মনে করো জিনাত মিস যতটুকু এরিয়াতে আসেন অতটুকু এরিয়াতে পোলাপান নাই, সো ইটস হার ইফেক্ট, সো সামথিং লাইক দ্যাট। It's a pretty weird example, right? I think
Not that.
It's an interesting one.
But does it make sense, man? Do you understand what the field means? The effect of something that is available within the region of space within which the effect is observable, that's the region space is what we define as field. And the strength of a field and the strength of a certain field is represented by means of field lines. Field lines are imaginary lines, and it doesn't mean that only where the field lines are there are field. It actually means that the field is pretty much everywhere, but we are using the field lines to represent them. I'm not going to draw any field lines because drawing a field would be pretty difficult. So if I just choose one of the simple figures, let's say maybe this one, copy image and paste, boom. So what I'm trying to show you over here is that this is a positively charged object. You have to understand that all three of these examples are infinitely apart from each other. So there are isolated charge in space. Isolated charge in space means that we are now observing a piece of charge which is unaffected by any other charge object in the entire universe. So we are only seeing this and there is nothing else. This is a way of observing things and without the effect of other objects that simplifies the observation and further ideas. So this is an isolated positive charge which is giving its field line outwards. Now you can see it has 8 field lines around it. It simply doesn't mean that the field is only working along this line and there is no field within this space. There is equal strength of field at the same distance from the charge, but we are using 8 lines over here to represent this field. So in comparison to this, if we had another field which has more field lines, that would mean that charge magnitude is bigger. For example, you can see one positive charge over here, one negative charge over here. You can see that both of these field has the same number of lines going out of them. So we can pretty much say that these two charges are magnitude wise equal. If this is plus 10, this is minus 10. However, you can see over here the field line number is far bigger. We have 16 field lines over here. So, I mean, I could count, yeah, there are 16 field lines over here. So if you wonder, I can say logically, just by looking at it, that this charge should be double than that. Even if it's not exactly double, it should be definitely bigger than that. And you can see it over here from this figure very well that positive field lines, positive charges are defined to give field lines outwards, and negative field lines are defined to have field lines inwards. Or in other words, you can say that field lines will always leave from the positive charge, or they go out of positive charges, and field lines enter into the negative charges. So these are the field line direction for individual charges if they are isolated in space. But whenever we're going to place two charges close by, we will have orientation like this. This is a good image. I'm just field line 2 to পড়ায় নেই তারপর তোমাদের ছেড়ে দিচ্ছি. Many of you might actually have to leave. This is 7:30 already. এটা হচ্ছে if you place two charges side by side and have a combined effect of them. So you can see that if you have two opposite charges, what's going to happen? Positive charges are going to leave out, but they are not going to be as straight as before, because earlier they used to be pretty straight. You can see it over here. Should I flip it? I think I can flip it. Flipping it may actually help us. Yeah. So yeah, this works better. So positive charge over here, negative charge over here. You can see here isolated charges were producing straight lines radially outwards. Radially means along the radius of a circle, radially outwards. But here the field lines are getting a bit of curve because negative charge is attracting the field lines, while the positive charge is repelling the field lines out. So they are actually taking a bit of curve and over here. And what is important that you can see that these field lines are shown to be broken lines. Field lines are actually never broken. The reason we actually draw field lines half a space, or we draw this kind of field lines, is to accommodate the figure within the given amount of paper space that we have. Actually এই field লাইনটা এখান থেকে কন্টিনিউ এখানে গেছে, এই field লাইনটা এদিক দিয়ে বের হয়ে অনেকখানি ঘুরে আলটিমেটলি এইখান দিয়ে এই লাইন দিয়ে ঢুকবে, এই field লাইনটা এখান দিয়ে গিয়ে অনেকখানি ঘুরে আলটিমেটলি এখান দিয়ে ঢুকবে। এই দুটো field লাইন যে মাঝখানে যে this horizontal field line, we theoretically say that these field lines are going to travel through infinite distance, but all the field lines are going to eventually curve and get back to the negative charge. That's the basic idea. And closer field lines represent a stronger field, further apart field lines represent a weaker field, which essentially means if you measure the distance between two field lines, if that distance is the locations where the field lines are, distance is close or distance is less, it represents a stronger field, which means close to the charge you have a stronger field. As you go far away from the charge, the field will be weaker. You can see it over here that close to the positive charge surface, the field lines are really close. The gap is very small. As you get farther away, the gap is increasing. Up to here, the gap is increasing. But from this point beyond, if you observe further right, you can see that the gap is decreasing, which means strong field becoming weaker, weakest field. Then as we go slowly to the right, field becoming stronger, 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 stronger. Once again, pretty strong field. Yes, Shaptoshi and Shafat. You really have to leave.
Sir, I have class now at
আচ্ছা ঠিক আছে,
7:30.
আমি ছেড়ে দিচ্ছি। I'll pick up from this very point. বলো সপ্তর্ষি বলো।
স্যার এই যে বেস লাইনটা যেটা আপনি বললেন যে দে ট্রাভেল অ্যাট ইনফাইনাইট ডিস্টেন্স, তাহলে যতটা বেশি ডিস্টেন্স বাড়বে ক্যান বি সে যে অ্যাট আ পার্টিকুলার ডিস্টেন্স দিয়ে এফেক্ট অফ দ্য চার্জেস গেটস নেগলিজিবল?
Yes, definitely.
ওকে স্যার।
Definitely. So this is the shape of the field lines that we have, which is the merge of two opposite charges field lines, and this is the type of field that we can have whenever we try to bring two similar charges close. Here, these two fields are pretty much identical in shape because assumably these two charges are equal in magnitude. But if we do not have equal magnitude of charges, we might have this kind of complicated cases. So last thing, I hope this looks good on our paper. It doesn't get black. Yeah, it didn't get black. So if we have unequal charges, then we can have this kind of, you can see over here, you can see, pretty much see from here, I mean between these two charges, which one do you think it has a bigger magnitude? Between these two positive charges, which one do you think has a bigger magnitude, left one or right one?
The right one?
The right one, essentially the right one, because it is producing more field lines. And you can see that now that this charge has so much strength that it is practically bending out the small charges field lines. That's practically what happens if you bring two unequal amount of charge close to each other. Same thing for the negative charges. Only difference is these field lines are outwards, these field lines are inwards. That's the only difference. And then if you have opposite charges, same stuff. Here the negative charge is strong, positive charge is weak, so you can see that the field lines are taking this kind of shape, and the other thing over here. You just have to be able to remember the shape of this type of field lines in the MCQ. Then field lines are mostly come in MCQs. They might give you 4 pictures of different field line orientations, and you have to pick up the one that is correct. So unless you are acquainted with how these field lines look like, it will be difficult for you to work with. And that's pretty much it for the field lines. And field lines have some 6 properties, which I'm going to discuss in the next class. আজকে এইটুকু থাক, ঠিক আছে?
স্যার মাথায় একটা কোয়েশ্চেন চলে আসছে, জিজ্ঞেস
বলো।
স্যার এই যে এখানে যে বললেন না যে রাইট ওয়ান ইজ প্রোডিউসিং মোর ফিল্ড লাইনস এন্ড লেফট ওয়ানটা কম, তো কি কি ফ্যাক্টরস এটা ইনফ্লুয়েন্স করে যে কতটুকু ফিল্ড লাইনস?
Well, the field lines are actually a relative way to represent the strength of the charges. It's not an absolute way. এরকম না যে 10টা field line মানে 10 কুলম বা হচ্ছে 100টা field line মানে 100 কুলম, ওরকম না। It's a relative way. So if you have within a figure 2 charges represented, and right off their surface, if they have dissimilar number of field lines coming out, then you can positively, then you can surely say the one that is producing more field lines out of its surface has a bigger magnitude, and vice versa.
Okay.
In another words, I can say that, let's say এই চার্জটার এক্স্যাক্টলি এই পজিশনে তোমার ফিল্ড লাইন্সের যতটুকু গ্যাপ, এই চার্জটা এই পজিশনে ফিল্ড লাইনের গ্যাপ তার থেকে অনেক কম না?
ইয়েস স্যার।
তার মানে এই পজিশনে ইলেকট্রিক ফিল্ড স্ট্রেংথটা অনেক স্ট্রং কম্পেয়ার টু এই পজিশনে ফিল্ড লাইন। তার মানে অবভিয়াসলি এই চার্জের ভ্যালু অবভিয়াসলি কি হওয়ার কথা? বেশি হওয়ার কথা। এই চার্জের ভ্যালু অবভিয়াসলি কম হওয়ার কথা। Electric field strength means the amount of effect, the force it can exert on other charged particles. Did I answer your question?
Yes, sir.
Acha. Pulman, thank you very much for the additional 6 minutes of attention. We'll see you again pretty soon. Among aske, I hopefully by now তোমাদের thermal সবগুলো lecture তোমরা YouTube পেয়ে যাবে if you want to revise those, and worksheetটা তোমরা hopefully আগামী ক্লাসের আগে পেয়ে যাবে. I'm sincerely working on it, and coaching এখন already আবার Dalal মাঠে shift হয়ে গেছে. So yeah, looking forward to it. Allah Hafiz. Assalamu alaikum.